The German mathematician David Hilbert devised a famous thought experiment to show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hard-working night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now, an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy, and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to room number 3 to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1. square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilbert's Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever-diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
Today, we just talked about cardinality. Specifically, we prove two sets have the same cardinality. So what is cardinality? Cardinality is basically the size of the set. Okay, it's the size of the set. In other words, how many elements are in there. So cardinality in this word means the number of elements in your set. Number of elements. So if we want to prove two sets have the same cardinality, we're trying to show that they have the same number of elements. For finite sets, you can just count them, right? You can just count, oh, they both have 3 elements, or they both have 10 elements. You can say, oh, they have the same cardinality. But for infinite sets, it's impossible for you to actually count, right? So we need to use something else, which is what we learned from before, that is, the two sets have the same cardinality if there is a bijection between them. It should make sense to you because bijection means 1 to 1 and onto, so every element from this set mapped to exactly one element from the next set. So each of the elements has something mapped to it. That is why, even though it's infinite, as long as they have a bijection in between them, that means they have the same number of elements. So whenever the question asks you to, for example, prove the following pairs of sets have the same cardinality, that means you need to construct a bijection between the two sets. Does that make sense? Because that's how you can show there are exactly the same number of elements in those two sets. So this should hopefully make sense to you guys. Yeah, also the drugs. I should every semester when I mention this, people go around spread the rumors that Lynn asked us to take drugs when we do cardinality. That's not my intention. I'm not asking you to take drugs to stay away from drugs, okay? That's not my intention. I'm just saying it's his work is impressive. That's what I meant. Anyway. So there is a theory in your textbook that says the set of naturals and the set of rationals have the same cardinality. This I'm not gonna prove it because the proof you can check your textbook. It's several pages long, so I'm not gonna do it obviously. Is the proof important? It's this important. This much important, tiny bit important. So what does that mean? It means that the proof itself was never ever tested on any quiz or test or final exam. But was there ever on any assessment? Yes. It showed up in homework before. Okay, so that means if you see a question like that in your homework, well, obviously you need to do it. Otherwise, you can forget about it. Okay, so the proof itself, not that important. The result is what's what matters for you. So you should remember the set of naturals and the set of rationals have the same cardinality. And we use this sign to denote cardinality. So it looks like the absolute value, but it's not. So hopefully when we put a set inside of those two bars, we would not think it's absolute value. It means they have the same cardinality. And this proof is building a sequence, remove, repeat, and in certain ways you do it. It's kind of like diagonal, but it's not diagonal. But this, you probably will never see it again unless it shows up in your homework. So you can sort of move on. But before we go to example 1, can someone come up with a few other examples that have the same cardinality with the set of naturals? Anyone? Yes. Integers, that's correct. So I'm going to write it here. Let's write it here. The set of integers, yes. Anyone else? Remember in the video, we moved every guest to what? To 1. So what does that map to? If I have a function mapping integers, so if I have this function, totally I'll leave it as a question mark because that's literally what I'm asking you. F of n equals to 2n. Then what is the image? Or what should I put my codoline as? Anyone? What does this function prove? Yes. Even integers, that's correct. Okay, so if you use this, you can see that So let's use E to denote even integers. We can see that, for example, 1 is going to map to 2, 2 is going to be mapped to 4, 0 is going to be 0, -1 is going to be -2, and so on. Okay, so we can see that we don't have odd integers anymore because we're mapping to 2n. Right, so this shows that, because this is a bijective function, this shows that the set of integers and the set of even integers have the same cardinality. Okay, and you can do a similar function. For example, let's map it to 2n plus 1. Right, then it maps to all the odd integers. So we can put the set of odd integers here as well. We usually use E to represent the set of even integers, O as the set of odd integers. So all of those have the same cardinality. Okay, except this one is hard to prove. This one is hard to prove. Everything else should be simple to prove. Should be like a relatively simple function, which you can think about. Especially this one. Think about how would you do it. Okay, you need a bijective function. Now let's do something slightly more complicated than that. So I want you to show the following pairs of sets have the same cardinality. Okay, so let's just do it. I'll give you, let's say, 5 minutes to work on all of them. So if you're completely stuck with A, try B, and so on. Okay, so do as many as you can. If you cannot do it, just skip it, because I want you to give a try on all of them. So give it a try. You first want to determine what the elements look like before you do anything else. Because if you don't even know what the elements look like, there is no way you can do the bijection. Any ideas? Let's see, which one do you think it's relatively easy for you? B? Okay. A is easy. B is easy. Anyone else? C is not easy. Who said A is easy? Raise your hand. I want to check your solution. Don't be scared. It's okay.
No, I was just tapping a little bit. I know that I know it's the integers, right? These the rationals.
A is not all the integers. Most of them are not integers. Okay, yes.
Could you do f of theta and f of x equals square root x?
F of what? Hold on. Say it again.
F of a to n, where f of x equals the square root of x.
F of what? N?
F of x equals square root x.
Equals to square root of x?
Yeah.
What are you mapping? What's your domain coordinate?
A and n.
From A to N?
Yeah.
This?
Yeah.
Or N to A?
One of them.
No.
No.
Yes.
Can you take some element from the A and square it, and then that would be in n? And you can have the same amount.
Take some elements and square it.
The function is like f of x.
Then I can tell you that's not going to be an injective function. Injectivity fails. For you, surjectivity fails. So, okay, let me take it up. It won't be easy. Don't worry about it. Right now, it might seem hard to you, but after I tell you the tricks, you'll find it. Hopefully, you'll find it easy. I cannot guarantee because who knows. When you see something like this, I would recommend you to first determine. I mean, here clearly they have the same cardinality, so it's L of 0, or it's the same cardinality with natural. Suppose you're given something and you don't know if it's the same cardinality with the natural. I recommend you to decide that first, because that part will determine which method you want to use. Okay, so now I'm telling you, for countable sets or the sets with the same cardinality with natural, this is how we can do it. And the way is you list them in certain order. What do I mean by that? Let's look at what A look like. So A, what do you think the elements look like? It's all the ones in real numbers such that A squared equals to A squared is a natural number. So for example, the first natural number is 1. A squared is 1, then what's A?
1.
That's the only one. A squared equals to 1, what's A? Plus or minus 1 is correct, right? So A, you have -1, you have 1. Next natural number is 2. So if a squared equals to 2, then what's my a? You don't know? Yes. Plus or minus root 2, that's correct. So root 2, let's use the negative one first. Negative root 2 and root 2. What about the next one? What do you think the next one will be? Yes. That's correct. So negative root 3 and root 3. And so on. And you continue because that's how natural numbers work, right? So that's why your function is not surjective because well we have negative ones here. And that's why yours is not injective because both of them will map to the same element using array. Okay, so you can see that your function is not going to work because of that. But now I can see clearly what I want to do. Instead of using rational, both of you are right. We don't want to use rational directly because rationals are ugly. We want to use the clean one, which is natural. Natural or integer, it's up to you. Whichever one is easier to use, just use it. So here, I'm going to say, let's say natural. Doesn't really matter. So natural is 1, 2, 3, 4, 5, 6, and so on. So if I write it like this, you can see that for my function, for my bijection, I want 1 map to negative 1. I want 2 map to 1. I want 3 map to minus root 2, 4 map to root 2, 5 map to root 3, 6 map to root 3. Okay, so 5 map negative root 3, 6 map to root 3, so and so on. So this is what I want my bijection to, the mapping to be like this. Okay, if the question don't tell you that you need an explicit bijection, then this is your function. Okay, if the questions just say, oh, should they have the same cardinality? They didn't say, should they have the same cardinality using explicit bijection? Then you can leave it like this. And with some explanation, you can say that there is no repeats, injective. Everything will be mapped to surjective. So this is a bijection that means they have the same cardinality. However, a lot of time we'll ask you for an explicit function. Okay, so in those way, I will tell you how do you come up with it. The key is still using this diagram. And what you need to do is you need to find the pattern. Okay, so the pattern is, I don't know if you noticed, but I noticed the even ones map to negative numbers, odd one map to positive numbers. Right? Agree? So I'm going to use a piecewise function. Okay? Piecewise function, my two pieces will be even odd. So let's write it down. So I have a f. Make sure you write your domain and codomain. So my domain is going to be the set of natural. My codomain is going to be a. And I'm going to define it as a piecewise function. What it is, I don't know yet. I'll figure it out later using my diagram. But I know the two pieces is when x is even and when x is odd. So far, so good. Do you guys see why I decided to use a piecewise function? Okay, so now let's look at the even cases. So let's look at the negative ones. First of all, I'm going to add a negative sign because all of them have to negative something. So it's there. Second, I notice that they are all under square root. The 1 minus 1 is basically this. Right, so everything is under square root. So let's put a square root here as well. So the problem is what's under square root. That's the only thing you can think about. So now, again, let's look for the pattern. I want 1 map to 1, 3 map to 2, 5 map to 3, 7 map to 4. So what function can do that? This is the part you need to think about it, okay? 1 map to 1, 3 map to 2. So you cannot just do minus 1 or something like that. Clearly that doesn't work. 5 map to 3. Yes. Plus 1 over 2, that's correct. So x plus 1 over 2 will do the trick. Do you see that? 1 plus 1, 2, over 2 is going to be 1. 3 plus 1, 4, over 2 is going to be 2. 5 plus 1, 6, over 2 is going to give you 3, and so on. Does that make sense? The first piece. Okay, yes?
So unlike the qualitative function, like this qualitative function, we have to show the function of bijection.
I'll talk about that in a moment. Okay, now let's look at the even ones. Now, again, 2 to 1, 4 to root 2. Again, they're all under square root again. And they're all positive, so I don't need to add the negative sign there. So now think about it. How do I map 2 to 1, 4 to 2, 6 to 3, and so on? 8 to 4. What do I need to do? Yes. X over 2, that's correct. You just need to divide by 2. So that's just gonna be x over 2. And that's my yellow ones. Okay? Is this clear? Okay. Now answer the student question. Do you need to prove it's bijective? Most of the time you don't need to provide a formal proof. You can just give some justification. What I usually do is I can use this diagram as my justification. I can see it, so we can say something like, we can see from this diagram that there is no repeats in the output. That means it's, no repeats in the input, no repeats, guarantees injectivity, and every number can be mapped to that guarantees surjective. So we don't need to give a formal proof. Okay? Unless we ask you to. So if you want a very formal proof, we'll let you know. We'll write it in the question. We'll say proof no bijectivity. Okay? Yes.
We also do from the domain starting at A.
Yes, of course.
Would it be harder?
Yes, that would be harder. So I always pick the easy way. So whichever one is easier for you, you do that. But we're not done yet. Okay? So I'm gonna say F is a bijection. But we're not done yet because this bijection tells you they have the same cardinality. But that's not what we need to prove. We need to prove the set of rationals have the same cardinality. So you need to use a composite function. Okay, so from just write something like this from textbook. We know that they have the same cardinality. So there is a bijective function. There is a bijection, let's call it G, that map from Q to N, for example. I don't need to write down what exactly the function is. I just know there is such bijection, and let's call it G. Okay, so now consider what? Consider the composition of them. So I want Q to A or A to Q. Maybe Q to A is easier. That's gonna be F compose G. F compose G is gonna map from Q to A. This is a bijection because composition of bijections is still a bijection. Remember you memorize the proposition? Is still a bijection. Okay, and now you can say they have the same cardinality. Make sense? So using the exact same technique, you can prove E. So I'll tell you E and A, they are the same question. They both require you to use composition. They both require you to list out what they look like, and you will see. I mean, E is slightly easier because you can easily map this to the set of rationals, and the rest is just rationals to even, which we talked about it before. Okay, so AE, same question. B, D are the same question. So, wait, why is my pencil not working? B, D are a similar question, but what I want to ask is C. Part C. How do you want to do it? Yes, go ahead. I don't know.
I did 100 by 8. I did 2, 4, 6, 8, 1, 2, 5, 7. Let's do this.
What if I ask you for explicit function?
We could do plus 1 over 2. Or minus, yeah, plus 1 over 2.
Plus 1 over 2?
Or plus 1. Plus 1.
Sorry, my pencil stopped working. I cannot write anything for some reason. Okay, let's try again. Plus 1 over 2.
No, it's still plus 1.
It's still not working. Why is it not working? Is it dead? Has no reaction. Okay, I'll tell you it's not gonna work. Why? Because E is the set of even naturals. F is a set of odd negative integers. They don't even have the same sign. Yes. F of x equals to minus x plus 1. What's your domain and codomain? So you want to map from E to F. Let's give it a try. Oh, okay. It's working again. Okay, so let's look at C. You want to map from E to F, and F of x equals to negative x plus 1. Is that what you said? Okay, let's try. Do you guys think it works? I think it works. So for example, again, we can draw the error diagram and see if it works, because that's how we deal with countable sets, remember? So we can try, let's say, 2, 4, 6, 8, 10, and we want to map to odd negative integers, so negative 1, negative 3, negative 5, negative 7, negative 9. So I want to do this mapping, and let's check this if this works. So I want to map 2 to negative 1. So negative 2 plus 1 is negative 1. Negative 4 plus 1 is negative 3, and so on. Okay, so again, to come up with a function, you're basically drawing the error diagram and using the error diagram to think about what do you want your function to be. Don't forget to state your domain and codomain. Okay, so that's C. Now let's look at B and D, because I said B and D are the same type of question. Why? Because they are not countable. Yes.
I feel like doesn't that codomain and domain are neither direction the same one?
Minus, yes, but you still need to state what your domain and codomain are. Yeah. It doesn't matter. The function is the same, but for a function to be well defined, you need to tell us what your domain and codomain are. Okay. So back to this. B and D, I said they are the same type of question because they are not countable sets. They do not. Okay, we were not uncountable, and I keep saying those words. No. I meant they don't have the same cardinality with the set of naturals. Okay, because they are reals. They are part of reals. So intervals, all intervals, just intervals, but all intervals, they have the same cardinality with the set of real numbers. So when you see intervals, you should know that they have the same cardinality and they don't have the same cardinality with naturals. So drawing arrow diagram is not gonna work. That's not how you do it. So how do you do those type of questions? Because I want to go over again. For intervals, there is a specific way you can do, which I want to talk about next time because I'm running out of time. But if it's not intervals, it's like with real numbers involved, or like real remove some part involved, or like real map to 2, 3, real map to -1 to 1, and so on. Those type of questions, you need to know the graph of the elementary functions. Okay, so the key here is you should know the graph of elementary functions. What are the elementary functions? The ones you see in calculus. So for example, so let me draw some graphs that you should know what they look like. Okay, for example, e to the x, exponential functions. Log x, logarithmic functions. Especially this one, we see this a lot, e to the x. 1 over x. You should know what they look like as well. We use it a lot as well. What else? Oh, here is a trick. Arctangent x. This one we use it a lot as well. Looks like this. And what's the horizontal asymptote? Anyone remember? Pi over 2, that's correct. This is pi over 2. This is negative pi over 2. This one is very useful. Just use function transformation to shrink it or expand it or move it. For all of those, we just use function transformation to deal with them. And of course, there is polynomials. This one. Okay, you can see the ones I draw. They all could be bijection within certain domains and codomain. Okay, so from those, for example, I didn't label this one. From those, which function do you think we can use for D? Which one is mapping from R to 0 to infinity? What do you want? The first one? Which one do we use for this? Yes, e to the power of x, exactly. Okay, so this one, again, write your domain and codomain. You can see that f of x equals to e to the power of x. Directly give you the answer. You don't need to come up with something really complicated. Does that make sense? Okay, let's say I want you to map from R to 0, 1. What would you do? Which function is better in this case to do that? Instead of 0 to infinity, I want you to map from 0 to 1. Which one do you think it's easy to deal with? Which one look like? Yes.
Maybe open interval 0,
Open interval 0, 1.
would it be?
R10, exactly. Okay, open interval A, B, this is the best option. Because it's already in this form, you just need to shrink it, right? Shrink it. So it gets to whatever you need. Okay, shrink it and move it up. Okay, so this type is about graph of elementary function. B, proof two intervals have the same cardinality. I need to spend more time on it, so we'll do that next time. I'll probably do the arbitrary one. I'll do A, B, C, we have the same cardinality. Yes?
For B, could you write C as 0 to 1 union 1 and D as 0 to 1 union 0?
Yes.
And draw arrows from the 0 to 1 and both.
Yes. This one is easy, so you can do it very easily. But if I give you something like this, it will be harder. Okay, so I want to prove the most general case next time. The next time we will do A, B to C, D instead of specific numbers. That's my goal. And with that, you should be able to do all of this. And this one, we already did it. I don't know why I put two the same question here. So similar question to this, we'll do that next time. And I'll see you guys next week. And good luck on your test. I do have 136 test. Is 137 test also this week? Anyone taking 137? Nobody? Nobody's taking 137? Wow. Okay.
Tennis question.
Hello? Yes? Someone said something. Oh, what's the attendance question? That's a good question. What do we want to do attendance question? Hold on, let me think about it.